Hi. Today we're going to go over exponential equations not requiring logarithms, and I have 10 examples. I have another video, I'll link it below if you need more about simplifying powers. And it started with the power rules and some examples. Let's get started and go over the 10 examples. I'm writing my notes ahead of time so I could save you some time and make the video short. Number 1. If you want to solve 3 to the power minus 2n multiplied by 3 by 9 equals 1 over 81. Notice that we have 3 and 9 and 81. So we need to think about the common base. What do I mean by the common base? As you could see, I'm using 3 instead of 9, 3 to the second, and for 81, I'm using 3 to the 4. So that's what I mean. We need the same base to finish the problem if we're not using logarithms. Move this up. I know sometimes we say like leave your answers in positive exponents, but in this case I want to compare left and right, so I want to have them all on top. So when you move it up or take the reciprocal, you have to change it from positive exponent to negative exponent. Now on the left we're going to add the exponents right there because we have the same base, just like we did in the previous video. So minus 2n plus 2, and that's what I'm using, this rule. Now, since I am comparing two powers with the same base, I should end up with the same exponents, so the exponents should be equal. This is what I mean. This implies that the exponents should be equal. Minus 2n plus 2 should equal to minus 4. And that's the rule. A to the power m equals a to the power n implies, or if and only if both ways, that m should equal to n. We're going to use this rule for all the 10 examples. Now after that simple algebra, we'll solve for n. We're going to subtract 2 from both sides. This cancels and we have minus 4. Subtract 2 will end up minus 6. Minus 2n goes down. Divide by negative 2, divide by negative 2. Left side is n, right side is positive 3, and that should do it. And that's the way I want to do it. I could do these all steps on the whiteboard, but it takes longer to record. And I could, instead of making 10 examples, I'm going to end up with 5 examples or less. So let's keep going. Example number 2. Now we need to think about the 216 and 6. So we need to think about 6 as a common base. So how many times I need to multiply 6 by itself to end up with 216? Here we go. 6 to the power 3 is 216. You could double check. So I replace 216 with 6 to the power 3. And now I need maybe to move it up. That's one option. Or I could apply this exponent and compare them from the denominator. But since I want to use that rule straightforward, I want to move everything to the top. No fractions. So I move this up and I have to change it to negative 3. That's the rule. So if it's positive and now it's up, it's a negative exponent or reciprocal. Same thing, 6 to the power 1. To see it as a power, when you take the reciprocal, you move it up differently speaking. That's going to be 6 to the power negative 1. We're going to apply the power of a power and apply these two exponents, negative 3 times negative k and negative 3 times negative 2, which is positive 3k and positive 6. That's a power of a power. Now we're going to compare these two exponents since we have the same base and the same rule applies. As you can see, we jumped to the exponents and we made them equal. After that, simple algebra. Subtract 6 from both sides. This cancels and I end up here with negative 7. Divide by 3 and that is the answer, -7 over 3. Let's go to example number 3. Now I have two powers with the same base, 3, but 81 is not base 3. We need to change it to base 3. 3 to the power 4, which is 3 times 3, 9, times 3, 27, times 3, 81. We'll make it all same base. So we changed 81 to 3 to the power 4, and now we're going to add the exponents right here using this rule. By adding 5p plus 2 and -5p plus 1, notice that those variables cancel, and I end up only with 2 plus 1, which is 3, as an exponent on the left. But in this case, I mean 3 to the power 3 is 27, and 3 to the power 4 is 81. We could see definitely that it's not true. But if you want to apply the rule, we end up with 3 equals 4, which is not true, so we say no solution. Example number 4. 64 to the power 5p equals 4 to the power -2p. We need the same base, so we could compare the exponents, and 64 is 4 to the power 3. Now we multiply the powers right here, and we end up 3 times 5p, which is 15p. Applying the power rule. Now we compare the exponents and end up with the following. 15p equals -2p, since we have the same base, and we're applying this rule. Add 2p to both sides to have the variables on one side. Right side is 0, left side is 17p. Divide by 17, divide by 17, end up with p equals 0 over 17, which is just 0. Number 5. This is ready since we have the same base, 4 and 4. So we're going to jump into the exponents and make them equal. I'm using different color here to highlight that and show you that this is our focus, the exponents. This implies that -3k equals 5k. Just applying this rule again. Add 3k to both sides to have them only on one side, and usually we get rid of the lower one to end up with positive and avoid using negatives. But either way will do. So this cancels, and I have 8k. Actually 5 and 3 is 8, not 7. My mistake. But the answer is 0, which is 0 over 7, or 0 over 8 is 0. Sorry, I don't want to go back and rewrite my notes just for that, or stop the video. It's a lot of hours of writing notes and cleaning notes, but eventually I end up with some typos, but my mistake. The answer is 0, and let's move on. I can't believe I did that, but it happens. Okay, number 6. Now, what do you think the base here is? 5, 25, 125? I think it's 5. So we could move the 5 up and make it 5 to the power -1. So we could compare and use that rule. 5 to the power 3 is 125. So I'm using two things right here. Moving this up using this rule. And instead of 125, I'm writing 5 to the power 3. Now here I'm going to apply a power of a power by applying the exponents. Same thing right here. Let's do that. -1 times 3n, -3n, and 3 times 2n is 6n. I'm thinking about if I have another typo. Hopefully not. Let's keep going. So 5 to the power negative 3n equals 5 to the power 6n. Now we could use the rule and go to the exponents and make them equal. Negative 3n equals 6n. That's this rule. Add 3n to both sides. Left side becomes 0, right side 9n. Not 8 or 7. Let's see. Yep, 9n. Divide by 9 to leave n alone. Or rewrite it this way. Now divide by 9. 0 over 9 is 0. Example number 7. Let's move this up. But what's the common base here? Notice that here is 1. And 1 is not base 3. But we could write it with base 3. Remember when we said a to the power 0 equals 1 and anything raised to the power 0 equals 1? So we could use the base 3. That's what we have. So we could rewrite 1 as 3 to the power 0. And we could move this up and make it negative exponent. Now we have the common base. On the left, we're going to add the exponents using the product rule. 3b and minus 2. So we're going to write 3b minus 2. Now we're going to compare the exponents and make them equal. And that's what I mean. Using this rule again. Simple algebra. We're going to add 2 to both sides, then divide by 3. So let's add 2. 3b equals 2. Divide by 3, and end up with 2/3. 3 more examples. What do you think the common base is? This is clearly 2, we can't change it, but 8 could be 2 times 2 times 2, 3 times. So instead of 8, we're going to write 2 to the power 3. Everything raised to the power 5x. We're going to multiply these exponents. That's called power of a power. 3 times 5x is 15x. That's what I did. A power of a power. Now we're going to compare the exponents. And we are going to say 15x equals 6x. Subtract 6x from both sides. This cancels and I end up 0 here. 15x minus 6x is 9x. Divide by 9 to leave x alone. And I get 0 over 9, which is 0. 2 more. The common base should be 4, because we could write 16 as 4 to the second. Of course, you could use all the way down to 2, but then you have to rewrite 4 as 2 to the second. So I could rewrite this as base 4, 4 to the second, and that should do it. Now, still we're going to raise that to the power negative 3n, so we're going to multiply the powers right here. That becomes negative 6m. I'm using different colors to highlight that and show you that now we're going to compare the exponents. Negative 6m equals 6. Divide by negative 6 to leave m alone. And we end up with negative 1. Our last example. 64 to the power 2n times 1 over 64 to the power negative 3n equals 16. So what do you think the common base is? Let's see what we could do. Let's move the 64 up first to have them without fractions, because eventually we're going to use that rule that compares them as without fractions. So by moving it up, it's going to be 64 to the power negative 1. And I still have this exponent. So I'm going to multiply these two exponents and make it positive 3n. Before we jump in and make the base the same, we could make this one part, one piece, one factor, and add the exponents. 2n plus 3n will make it 5n, but same base, 64. That's called the product rule in powers. Now we need to think about the 16 and the 64. Should I go all the way down to 2, or 4 will do, or 16? 4 will do, because 64 is 4 times 4 times 4, 4 to the third. And 16 is 4 to the second. So now we have the same base, but we still need to simplify here and multiply these two exponents. 3 times 5n is 15n. Applying the rule that we talked about, we have the same base, so the exponents should be equal because those two powers are equal. So this implies that 15n equals 2, and that's the rule. Divide by 15 to leave n alone. The answer should be 2 over 15. And that should do it. Thank you.
Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.